Okay guys, so in the previous class I started the formulation of dynamic equation of the robotic systems, and I came up at the end by introducing the Lagrangian equation. I started with this 2D graph rhythm robot, so I'm gonna just go over it to make sure everything is right, because I'm continuing. I assigned you as homework, but I'm gonna complete it because I'm gonna move it to the MATLAB. So we have 2D graph rhythm robots. It's k gonna be 1 from 1 to 2, and these are the kinetic energy for mass 1, for link 1 and link 2. So R1 was L over 2 cosine sine, R2 was this distance plus this distance, that's right. So L2 over 2, so theta 2 plus theta 1, that's right. And this distance plus that, so VC gonna be time derivative of this one. I'm gonna just double check to make sure everything is right. That's right. And the VC2 is the time derivative of the R2, so it's gonna be minus and now this term gonna be yep. So we need VC1 square, VC2 square, I mean magnitude, so it's gonna be VC1 square obviously gonna be L1 squared to the 1 over 4. This is gonna be 1. Here we're gonna have L1 theta dot 1 plus this square and plus this square, gonna be L over 2 over 4 theta square, and plus in this and in this, that's right. So it's gonna be 2 L1, 2 with 2 goes to Denver, L1, L2, to the dot 1, the same here. Sine in sine and cosine in cosine. If you know, we know from trigonometry that cosine A minus B gonna be plus between them. So this gonna be cosine theta 2. That's right. So having that, we move to the final for VC1 and the final for VC2. See, L1 and L2 over 2 for double check, and finally L1 L2 to the dot and cosine theta 2, right? Yeah. So now going to the other terms of the kinetic energy, that is the rotational motion. So we have to calculate omega 1 respect to 0, with if here obviously theta 1, and omega 2 respect to 0. I use the formula that I taught you a while ago. This is the formula that you have in your notes. So omega with theta dot, omega dot is theta dot plus R0 respect to 1, omega dot respect to 1. So, and we set up the coordinate frames, and R1 respect to 0 can be done like this, because here is theta 1, here is also theta 1. As you see, this is the rotation matrix. R1 respect to 0, cosine sine 0 minus sine cosine 0 0 0 1, and finally we came up with this. That's right. So T1 gonna be its translational part as we derived, plus its rotational part, because this is the planar robot. The mass moment of inertia is around the z-axis, right? So it's gonna be 1 over 2 this plus 1 over 2, you know from dynamics, this around the mass center, the 1 square. So this is gonna be 1 over 8, it's gonna be 1 over 24, and 1 over 6, as we already did. This is the kinetic energy for the link 1. So for the link 2, if I want to continue the problem, for link 2, let me go to the link 2. For the link 2 of the robot, 1 over m2 LVC squared that we had from here, from the previous class, right? L2 over 4 square plus this. There we go. That's right, cosine theta 2, and plus 1 over again IZ in what? This is the total theta dot 1 theta 2 square. That's right, and this is P, and this is P2. That's right, because this is a kinetic potential energy, and as I taught you, and this is the potential energy for the length. So what we're gonna do now, we have to say L is equal to sum of the T's minus sum of the P's. That's right. Let us do that in the next page. So L is equal to sum of the P's. This P is this 1 over 6 m1 L1 squared, so it's 1 over 6 m1 L1 squared theta dot 1 squared plus T2 is this term, right? This term 1 over 2 m2, that's right, 1 over 2 m2. Now the total of this L1 square theta dot 1 square L2 over 2 over 4, right? So theta dot 1 plus theta dot 2 square, yes, plus this plus L1 L2 theta dot 1 multiplied by theta dot 1 plus theta dot 2 cosine theta 2. This is the first part of T2, right? Plus 1 over 24 m2 plus 1 over 24 m2 L2 square, right? Multiplied by this, multiplied by theta dot 1 plus theta dot 2 square, right? So let me double check with you. This is what it is. M2 L1 2 L2 plus 2 square over 4 theta dot 1, so plus, I'm driving with you, okay? Plus 1 over 24 m2 L2 squared theta dot 1 square, and this is, so this is T minus P's. P's are M1G L1 over 2 sine theta 1 minus this part minus this part minus M2G M2G L1 sine theta 1 plus what? Plus L2 over 2 sine theta 1 plus theta 2. Here we go. So this is your Lagrangian function. Now we have to use the formula I taught you to drive the equation of motion. We have a long way, and I intentionally do that to tell you why we need the classical method, okay? After going to the MATLAB. So we have to use, hold on. So we have to use d over dt, partial derivative of Lagrangian with respect to theta dot k, because we have 2 theta, minus partial derivative with respect to theta k is equal to control torque that I'm going to design, hopefully. We have time, okay? So first going to be theta 1. So we have to calculate this. We have to calculate round L over round theta dot 1 and the round L over, because you have 2 equations, that's right, theta 2. Now we have to look at here. Theta dot 1, we have 1 over 3 m1 L1 square theta dot 1 we have here. Another theta dot 1 plus m2 L1 square theta dot 1. We have another theta dot 1 here. Gonna be plus m2 L2 over L2 square over 4, and it's gonna be theta dot 1 plus theta dot 2, right? Yes, hold on. Okay, so and now here we have theta dot 1. See here, we have multiplied, so what we get is this plus. Now let me delete this because I need space. Plus L1 L2 cosine theta 2. So it's gonna be 2 theta dot 1 plus theta dot 2, right? After the partial derivative, right? And we have 1 over 2 m2. This is equal to, and in the m2 divided by 2. Right? m2 divided by 2, L1 L2. So this cosine theta 2, theta dot 1 is squaring on theta 1 and theta dot 2. And still continues. We have here again plus 1 over 12 m2 L2 square, again theta dot 1 plus theta dot 2. Here we go. Yes? Do we have theta dot here? No, don't have. Here, respect to that, this is nothing we do here, we have it. It is m2 L2 over 2 over 4 theta dot 1 plus theta dot 2, because this 2 with 2 that goes to New York, so it's m2 L over 2 theta dot 1 dot 2. Here we have 1 theta dot 2, see here, plus m2 L1 L2, side theta dot 1 cosine theta 2 divided by 2. It is, just double check at home, you see, right? Only we have theta dot 2. Yeah. And again we have it here, plus 1 over 12 m2 L2 square theta dot 1 plus theta dot 2, right? Yeah, so that's it. But obviously I can't summarize them, because round L over round theta dot 1 round Lagrangian over round theta dot 2. See here, this term with this term with this term with this term with this term. So what we get is this 1 over 3 m1 L1 square plus m2, sorry guys, plus m2 L1 square plus m2 L2 square over 4 plus m2 L1 L2 over 2 cosine theta 2, and this 2 with this 2 goes to hell, so what you get is 2, we don't need that, right? We don't need that. Let's do it this 2 and that, and here 1 over 12 m2 L2 square in theta dot 1. Yes, and now theta dot 2 gonna be, let me change the color. See, you have theta dot 2 here, theta dot 2 here, and theta dot 2 here. Gonna be plus m2 L2 over 2 over 4 plus m2 L1 L2 over 2 cosine theta 2 plus 1 over 12 m2 L2 square. This also is theta dot 2. So let me double check. Yes, yes, and yes, right? And this is equal to the next line, theta dot 1, theta dot 1, theta dot 1. What you get is this, m2 L2 over L2 square over 4 plus m2 L1 L2 cosine theta 2 divided by 2 plus 1 over 12 m2 L2 square in theta dot 1 plus, we change the color, only theta dot 2 is this here and this here, so gonna be m2 L2 square over 4 plus 1 over 12 m2 L2 square over in theta dot 2, right? Right, so you see that I can simplify this more. I can add this with this. Also I can add this with this. I can also add this with this, and obviously this. So final writing, Lagrangian with respect to theta dot 1 gonna be, I'm writing 1 over 3 m1, and you can factor out L1 square from here, so let me write like that. Gonna be L1 square 1 over 3 m1 plus m2 plus 4 divided by 1 over 3 m2 L2 square, this is plus, right? 4 square plus m2 L1 L2 cosine theta 2 in theta dot 1 plus 1 over 3 m2 L2 square plus m2 L1 L2 cosine theta 2 divided by 2 in theta dot 2. Now round L over round theta dot 2 after simplification, this line gonna be again 1 over 3 m2 L2 square plus m2 L1 L2 cosine theta 2 divided by 2 in theta dot 1 plus 1 over 3 m2 L2 square theta dot 2. Bingo and bingo. I hope I didn't make mistake, but I'm pretty sure. I'm not God. I can make mistake because I'm driving with you. So we derive that. Now remember that the Lagrangian equation was this. Lagrangian Equation, time derivative of round L over round theta dot k minus round L as theta k is tau k. So we derive that round L over round theta dot 1 we derived from previous case. Let me change the color. Was here was m1 over 3 plus m2 L1 square, right? This term plus 1 over 3 m2 L2 square plus m2 L1 L2 cosine theta 2, that's right, in theta dot 1, right? Plus 1 over 3 m2 L2 square plus m2 L1 L2 m2 L1 L2 cosine theta 2 divided by 2 in theta dot 2, and we got that round L over round theta dot 2 because I need it here. That's right. Let me double check. It's gonna be 1 over 3 m2 L2 squared, the same term, plus m2 L1 L2 cosine theta 2 divided by 2 in theta dot 1 this time, plus, right, plus 1 over 3 m2 L2 square theta dot 2. So you can put each of these here and you get two equations, but before that we need this. So round L, or partial derivative with respect to theta 1, not theta dot 1, theta 1 based on either, do you have theta 1? No. Only theta 1 that we have here is this, and is this, and is this. Gonna be minus mg L over 2 cosine theta 1, yes, partial derivative, minus m2 gl minus m2 gl1 cosine theta 1, right? This is high school mathematics. And minus m2 gl, I'll do over 2, minus m2 g L2 over 2 cosine theta 1 plus theta 2, right? So you can simplify this as this right here, guys. You can say minus g L1 cosine theta 1, that's right, gonna be L1 over 2, sorry, it's gonna be, we are out of L1, gonna be, this is M2, gonna be M1, gonna be M1 over 2 plus M2, here we go, that's right, minus M2 G L2 over 2 cosine theta 1 plus theta 2. So here we go, right? Yes. Yes. And now round L over round theta 2 gonna be, again from here, theta 2, we have 1 theta 2 here, guys. See here, 1 theta 2. Gonna be minus 1 over 2 m2. Why minus? Because cosine gives you minus sign. L1, L2, theta dot 1. So gonna be L1, L2, theta dot 1. Theta dot 1 plus theta dot 2 sine theta 2. This is time derivative, a partial derivative of that. That's right. And this one. And this one. We have to do here. Gonna be minus m2g L2 over 2, again cosine theta 1 plus theta 2, right? Clear? So now we have it. Bingo. Now time derivative of each of these and these. So let us do that. And now we are drawing equation of the motion for this tooling robot. So times it's gonna be, let me say this as this term for simplicity. I name it as A1. So time derivative of this gonna be A1 theta double dot 1 plus, let me name this as A2. Do you care? No. So A2 theta double dot 2. So we did this word minus theta double dot minus, now this part round this, and now we're talking about minus this, minus in minus plus g L1 cosine theta 1 in m1 over 2 in m2 plus m2g L2 over 2 cosine theta 1 plus theta 2 is equal to what? Torque that we are applying to the joint to control the position of the joint. Now the second line, we are talking about this derivative of this, because exactly this and A1 they are the same, A2 they are the same. Look at here, we're gonna have A2 again theta double dot 1 plus, I name it A3 for simplicity, 1 over plus A3 theta double dot 2 again minus this plus m2 L1 L2 theta dot 1 plus theta dot 2 divided by 2 sine theta 2 plus m2 g L2 over 2 cosine theta 1 plus theta 2 is equal to torque. Understand? Yes? Okay. So are we done? Yes, we are done. We derived the equation of the motion of 2 degree of freedom robots. So you see that because we have 2 degree of freedom, we have 2 equations. theta dot 1, theta dot, and they are coupled, dynamically coupled, guys. We have everything in this line. They are dynamically coupled. That's right. They are dynamically coupled. So if you have 3D graph freedom robot, we're gonna have 3 equations interconnected. If you have 4, if you have 7 like Baxter and lab, we have 7 equations. If you have 10, 18, we have 18 equations. But these are not useful until we transfer it to MATLAB. And how we do that? Now I'm gonna take you back to your high school linear algebra. I can write this equation, right? As what? As what? Guys, there's a mistake here. Hold on. Huh, I'm getting older. I see that something is wrong. Oh my god. Okay, it happens. I see that something is very simplified. So guys, time derivative of this. See, time derivative of this. Because you have to do here, time derivative of this, a1 in this, and time derivative of this in this. So you're gonna have 2 terms. You're gonna have minus m2 L1 L2 theta dot 2 sine theta 2 in theta dot 1 derivative of this, that's right, plus now a1 in theta dot 1, first in second, second in first, that's right. I'm getting older, guys. The same valid for here. It's gonna be minus m2 L1 L2 theta dot 2, that's right, sine theta 2 divided by 2 in again theta dot 2, now plus a2 in theta dot double dot 2, that's right. First in second, second in first, that's right. Now this is equal to tau 1. I see that I was missing. I was wondering what was that. The same for here. You get minus m2 L1 L2 theta dot 2, the time derivative, sine theta 2 divided by 2 theta dot 1, plus now again a2 in theta double dot 1, plus now we can say a3 in theta dot 2. Huh? Am I stupid? I forgot this again. Plus GL1 cosine theta 1 and 1 over 2 plus m2 plus m2g L2 over 2 cosine theta 1 plus theta 2 is tau 1. Now I forgot the potential term. But this is good. Why? You see that even a 2D algorithm robot, you can easily forget something in trivial thing in algebra. So that's why we need classical method to derive the equation of the motion, avoiding this huge mathematics. Okay. And now let me double check with you. Minus m2 L1 theta dot 2 cosine theta 2 theta dot 1 a1. Minus m12 because so 2 theta dot 2 a2 theta dot 2. Good. And minus plus g plus m to g. No, this is fine. So and now the rest of this, let me double check this. Yes, and now plus these terms, right? M2 L1 L2 theta dot 1 in theta dot 1 plus theta dot 2 divided by 2 sine theta 2 plus M2 G L2 over L2 over 2 over 2 cosine theta 1 plus theta 2 is tau 2. Equation number 1 now, equation number 2, we derive that. But if you want to transfer this equation in MATLAB, you have to do some tricks. First of all, you have to write in standard notations that I'm teaching you right now. Remember, in the vibration course, we had this equation, remember? Mx double dot plus Cx dot plus Kx, mass spring damper is equal to F, remember? This is what mass, this is what damping, and this is what stiffness. Remember the names? Do I have time? Yes. So now in robotics, instead of mass, we say mass matrix. Mass matrix. Instead of damping, we say Coriolis matrix. Here is a stiffness matrix. So we have to write our equation like this, guys, as a vector theta double dot 1 theta angular acceleration of first joint and second joint. Now let us look at here. First equation, so here gonna be A1. So see, for theta double dot, the first line is A1. A1 is a huge term by itself, that's right. This is A1, right? So what about this is 2, theta dot 2. In the first line, theta dot 2 is A2. See here, A2. What is A2? A2 is this term. It's changing with time. It's time varying because that's cosine theta 2. Right? Do we have another theta? No, we don't have. Now to the next line, the next equation. Theta double dot 1 is A2 again. Here is A2. Theta double dot 2 is A3. This is theta double dot 2A is A3 is this, guys. Don't misunderstand. This is A3, right? Gonna be A3. Oh, now we are writing in the matrix form, as you have to do, because when you are coding in MATLAB, you have to write like this. There is no other way. Okay? Understand? So, clear? Okay. I mean that if you want to write in the ODE format, if you want to write in ODE format, you have to write like this. If you don't want to write it, good luck. Okay, so see that they are the same. Non-diagonal, they are the same. So now this is what you tell me. In the literature, we name it as mass matrix, capital M, or sometimes we say D. Okay, this is mass matrix because it's a coefficient of acceleration in terms of the joints. Plus Coriolis matrix. Why? Because it is, let me write it here, guys. Plus Coriolis matrix. This is because plus now theta dot 1 and theta dot 2. Here we go. See, theta dot, we are coming down to x double dot x dot. So let us look at the first equation. Theta dot 1 is this, its coefficient, right? You can write like this, huh? And theta dot 2 is this, you can write like this. So it's gonna be minus m2 L1 L2, right? Theta dot 2 sine theta 2, say theta dot 2 sine theta 2. Now theta dot 2 is the same but divided by 2, minus m2 L1 L2 theta dot 2 sine theta 2 divided by 2. See here? See here? So next line gonna be exactly the same, like that. Minus m2 L1 L2 theta dot 2 sine theta 2 divided by 2. And now this is one term. We have another terms, guys. We have see, this multiplied by this gonna be plus m2 L1 L2, so gonna be plus m2 L1 L2 for saving space, L1 L2 sine theta 2 plus 2 sine theta 2 divided by 2. That's right. Yes. See, I'm talking about this. And now theta dot 2, only term we have is this. Gonna be the same. And we have theta dot 1 here. 1 theta dot 1. Theta dot 1 multiplied by this. Right? And now the other term gonna be the same in here. Gonna be again m2 L1 L2 theta dot 1 theta dot 1 sine theta 2 divided by 2. The name of this is Coriolis Matrix, and we are showing with C. As you see, is a function of the angles and the angular velocities, guys, and the angular velocities. That's why in the literature for robotics we are showing Coriolis as Q and Q dot Coriolis matrix. Okay, as Q and Q dot. And finally plus a stiffness matrix. A stiffness matrix. Why? These are our stiffness matrices. This first line I'm naming it as B1, the total of this, look at here, a total of this B1, and I'm naming this as B2. So this is gonna be B1 and the B2. These are a stiffness matrix. We are showing with K. This is equal to torque that we are applying joint 1, torque we are applying to joint 2. Now we can transfer these in the OD format to MATLAB. Okay, so I'm gonna do that the next class.